assumption on this equation is that ck, so the coefficient that's associated with a n minus k cannot be 0. The other ones can. A1 can be 0, C1 can be 0, C2 can be 0, just except ck. So that is the last term you will have. And to solve this kind of recursion and get what an is in the closed form, we are trying to start with the assumption that an equals to r to the power n. So this is a very general form we can assume, and we can plug in that original recurrence, and then we have the new recurrence, Rn equals to C1 Rn minus 1 plus C2 Rn minus 2. So this is an assumption, so we have to verify that later. But this is essentially an assumption when we assume an equals to r to the power n. And once we have that equation, we are trying to simplify it by dividing both sides with r to the power n minus k. So this is possible because we assume that r is not 0. Okay, otherwise, if r is 0, then it would mean an is 0. Without spending time on running algorithm, which is obviously absurd. So in that case, r is not 0, then r to the power n minus k is not 0. We divide that on both sides, and then we get rk minus c1 times rk minus 1, and so on and so forth equals to 0. So we call this equation the characteristic equation of the recursion, and then we call that the values of r that satisfy the equation the characteristic roots. So it's the solution to the equation. And the original closed form for an can be derived from the roots, the characteristic roots of its characteristic equation. So that's what we are going to look at. And I mean, if you simply memorize that, it's okay, but we're gonna go a little bit more to understand why. So a very special case is when we have degree k equals to 2. In this case, we have a form an equals to c1 times an minus 1 plus c2 times an minus 2. So this is a special case, a special case for the linear homogeneous recurrence. So with this case, we will have a simpler closed form solution. And what that is we can say if we have this form, then the solution for the recurrence will be an equals to alpha 1 times r1 to the power of n plus alpha 2 times r2 to the power of n. So here, alpha 1, alpha 2, these are constant coefficients, so they're not a. Okay? So don't mess up with a, these are alpha. So this one is different from this one. Okay, from a. And then the r1, r2, these are the different roots of the characteristic equation. So they are the characteristic roots. So you imagine that if the degree of the equation is 2, right? If that is the original recurrence, and that is the characteristic equation with a degree 2, then you would have either one single root that are the same or two different roots. Okay? So this case applies when you have two different roots, r1 and r2. So it would directly tell that the closed form for an is alpha 1 times r1 to the power of n plus alpha 2 times r2 to the power of n. Okay. Any questions at this point? Okay. So there are two tasks we need to show. The first one is, of course, we want to verify that the claim is true. That means we want to verify that this closed form for an is indeed a solution for the original recurrence. An equals to c1 a n minus 1 plus c2 a n minus 2. Another one is we said that alpha 1 and alpha 2, they're constants and they're coefficients, but we have not been able to determine because we only solve the characteristic equation and only get the characteristic roots r1 and r2. We don't know alpha 1 and alpha 2. Okay. So to complete the computation, we have to also find out the values for alpha 1 and alpha 2. Okay. So the first thing we want to show that the solution is correct is we will simply plug in our conclusion to the original characteristic equation. So this one, as you see, is the characteristic equation, And then because R1 is a root of the equation, R2 is also a root of the equation, so we can simply say, you know, R1 squared equals to minus C1 R1 minus C2 equals to 0, which means R1 squared equals to C1 R1 plus C2, right? And R2 is also a root, so it's fair to say R2 squared equals to C1 R2 plus C2. So these are the ones that we can have based on the fact that R1 and R2 are the roots of the equation. And what's next is simply start with C1 times AN minus 1 plus C2 times AN minus 2. So this is the right-hand side of the original recurrence, right? So the original recurrence was AN equals to C1 AN minus 1 plus C2 AN minus 2, right? So remember, this is the original form of the recurrence. So we start with the right-hand side of the recurrence by plugging in these equations for R1 and R2, and eventually we get AN. So it means that I'll skip the entire process because I think it's a simple expansion of some terms. But the key point is that we can go from the right-hand side of the original recursion to the left-hand side of the original recursion by plugging our conjecture of the form of the closed form. Okay. So in this case, we can show that, okay, this AN equals to alpha 1 R1 to the power of n plus alpha 2 times R2 to the power of n is indeed a correct form for the solution of this linear homogeneous recurrence of degree 2. So that's very special for degree 2. When we're moving from degree 2 to, for example, in the case of degree 2 where we have two identical roots or we have higher degree, then you will have other solutions. So that's what we have for the rest of the slides. Right? So this is the case when you have identical roots. And then this is a case where you have general more than 2 degree of 2. So let's go back to the original one. So next, any questions? Any questions before we move on? The next task would be, as I said, to solve for the values of alpha 1 and alpha 2. So we know that the recurrence has to, be generic for all cases, where it has to apply for AN, has to be applied for A1, A0, and so on and so forth. Every special case, it has to apply. So to solve for alpha 1 and alpha 2, we simply try to use the fact that we can easily measure the values of A1 and A0. Okay, so in this case, we have A0, and then in this case, we have A1. So in this case, we know the values of R1 and R2. We know the values of C1, so C0 and C1. So we would be having, this one we know, this one we know, this one we know, and this one we know. So in this case, we would be having a equation system that has two equations, and we're trying to solve for two variables, alpha 1 and alpha 2. So in this case, we can just determine the values uniquely, and then we would simply say alpha 1 equals that, and alpha 2 equals that. So C1 is the running time, or the number of steps we run when the index of the series is 1, or in other words, A1. We try to solve for AN, but we know A1, A0 very easily, and C0 is for A0. So these are conditions that you want to find either in practice. You would run your algorithm with a very special case, right? Just run your algorithm with a program with one single input. Or if you're talking about solving a question in exam, then you should just find that boundary case. Okay? So what if you're inputting a value of 0, so you just respond to the exit condition of your recurrence, the boundary case. What if we only have one element, like merge sort, what we do with only one element, return. So what's the effort for the return, right? And if a 0 element, you return what is the element again, the runtime return. So right. Any questions? So the rest is, if you have only one root and then what's going on, and then if you have more than two roots, you have more generic degree k, what will be happening? So those are whatever the equations you can use for solving linear homogeneous recurrence. So I won't be testing for any cases that's more than two. It's like, I think it's hard to solve a degree 3 equation, and then not to mention that there's k degree. So this is just for reference if you need them in the future. And let me just let you know that there's a way to solve this generic form, but I won't test the generic form in the exam. But I do reserve the right to test degree 2. Any questions?
I was wondering if you could just kind of go over like what the final exam will look like. I don't know, like how similar it is to the midterm and how long.
Yeah, so it'll be the same form as the midterm. So we'll have 5 questions. Very similar 5 questions, and then so I'll say maybe each question is longer than the midterm that we have. So like 3 or 4 sub questions. So they're all related. Like for example, we talk about like I don't know, nitrous algorithm, right? So we'll be saying start with the proof, start with writing the algorithm, the pseudocode, the proof, why it's correct, and then generalize it to the using induction and so on and so forth. So those 3 or 4 sub questions will relate to the same theme, same topic, but there will be 5 big questions, each big question with 2 or 3 sub questions. Or like analyze time complexity. So speak of the content, I think there are like 40 or 35 to 40% of the content will come from part 1, meaning things that we learned before the midterm, and then another 65 to 60% come from the second half of the course. Yeah.
Well, so like the proofs part of the exam will those mostly be proofs that we talked about in class?
Yes. Yes. So here's that. So I mean, so if I want to analyze like time complexity or something, you will still treat that as a formal proof. I mean, depending on how you think about it, you still have to present it correctly. So I'm not sure if that counts as proof, but if you count it, then no, right? Probably you have some other algorithms that you have analyzed time complexity, like the solve recurrence. Right? So you would have to, if you say that I give a time complexity for recurrence, I kind of try to prove it, right? So, but it's not what I think what you mentioned is a proof of the correctness as the other things. Right? So yeah, so most of the proof, if you think about the correctness of the proof, that will come from the slide, but in a more generic form.
Should we be focusing more on formal or informal proofs?
So you don't need any formal proof in the final. So, but the thing is, even though you don't need any formal proof, the informal proof will still need to be correct. I mean, you will still have to follow the guideline. You will still you can only present propositions where each sentence you can, determine its truth value unambiguously. You will need to follow the correct form of inference. You will have the premises, the conditions, and so on. It doesn't mean that it doesn't mean that if we don't need formal proof, then the informal proof can be, informal or incorrect in that sense. Right? So you still have to give sound or correct informal proof in that case. Any other questions? Yeah.
So what all the proofs? I mean, like algorithms would we need to know for the final? Basically, like Dijkstra's and like.
Yeah. So all the algorithms that we have discussed either in the slides or in the homework. So I think that includes the GS algorithm for stable matching, and also the other algorithms that we talked about, Dijkstra's and I think the quicksort, things like that, the topological ordering that we just talked about, and the other ones that we haven't talked about.
For any like pseudocode questions, because they're lengthy, similar to ones that we had in one, or right at the pseudocode algorithm.
Yeah. So for when I say design algorithm, whatever, I'll say that you actually present a pseudocode in the algorithm. So I mean, I will try to discuss that while we do the exam. I can talk about that right now. So for each question, I would try to be more specific to what you need to do. So, for example, I would say here, devise an algorithm. I'll have the parentheses saying as pseudocode. I would say analyze the time complexity. I would underline the analyze keyword. So you would present your analysis. I would say prove, right? Prove the correctness of something. So just underline that proof, even though that you need proof. Or as pseudocode, or if I said explain, that would be very generic. You don't have to be that formal as reading a proof. Explain would be just simply saying why we need learning scores and something like that. What else do I have? Or like give definition of something. So underline then give definition, so you know what it is. Right. So I think it would be more clear to follow in a final note. Just underline the thing that you need to do for each submission.
When you say analyze time complexity, you're just looking for big O notation, right?
Yes.
You'll ask specifically if you want big omega or big theta.
No. So if I only say time complexity, it would be big upper. All right. Any other questions? So I think I promised to talk about the homework 6. If you guys have no more question, I'll go with homework 6.
I just had one more question about the exam.
Yeah.
Is there any like really big topics that we should for sure be like focusing in our studies? Because I know we need to really be studying everything, but is there like a really big topic that like, we really should be focusing on understanding well for the exam?
Well, I mean, we have only learned like 3 topics, right? So I think module 1 we learned how to prove. I mean, that's big. Of course, you need to know how to prove, right? But the scope is restricted to the examples that we have read on. And then another big topic is how to analyze time complexity, right? And then the third topic is how do you find the relations among subproblems and develop recursion. Right? So I mean, we only have those 3 big things, so I guess all of them important. All right. Any other questions?
Can you go over, kind of related to the homework, can you go over the n squared integer multiplication?
Yeah. Sure. Yeah. Okay. So I'll start the integer multiplication problem first. So if you think about an integral multiplication problem, so we are assuming that we're trying to multiply 1 to 12 with 30. Right? So, I mean, if we do it in a standard way, we are trying to multiply 4 with 2, we multiply 4 with 1, and then we multiply 3 with 2, and 3 with 4. Right? So, I mean, in that case, for every digit in the second number, we have to multiply that with every digit of the first number, and go over that for every single digit of the second number as well. So it's very obvious that it's a O(n) squared on complexity, right? If we have n digits in each number. So the divide and conquer case is if we're trying to split if this x is y, x0 is 1, y0 1. If we try to use the recursion or divide and conquer to split the entire set of digits into two halves, what we're trying to do is the same. So we would treat everything right here as a digit. That's a longer digit. And this one also one digit, this one as well. So what we'll do is we'll say that x times y would equal to, so x0 times y0, and then times 10 to the power of n over 2. Right, so because these are with higher significant digits, and each digit right here means 10 to the power of 2 in the real case. Right, so if you think about that, 1 here means actually 10. So you have to multiply that 10 to the power of n over 2. Right, so of course, if you think about a decimal system, if you are talking about a binary, then just replace that with 2. And then the plus x1 times y0 times 10 this should be 2 n to the power 2, and then plus x0 times y1 times 10 n to the power 2, and then plus x1 y1. Right. So we have two multiplication there because we have x0 and y0 both being with higher significant digits. We only multiply 1 here because we only have y0 associated with a higher digit, and we only have 1 here because only x1 is associated with a higher digit. So in this case, we see that this is also no problem for multiplying two values, and this is also a multiplication problem, right? We multiply x0 with y0. This is the same, it's the same, and it's the same. And we know that before, if we have n digits for x, we now have n over 2 digits for x0, for x1, for y0, for y1. So each of the subproblem will have half of the size of the input as before. So if this is, we need Tn for solving the multiplication of two n digit numbers, then we need 4, so 1, 2, 3, 4. 4 subproblems with half of the input size, right? And then we know that we need to add them together. These are the additions. So we know that if we try to add n digit numbers, then we need to spend O n times add digit by digit. Right? So that would be the growth function in the recurrence form. And if you plug in this to the method theorem, you will realize that's so this is nothing better than doing digit by digit, except that we don't need that many digits to actually store the values inside. we can do it addition instead of multiplication. So that's original n squared kind of compressed out. So to for the homework 6, we are asking for generating a O n log 3 time algorithm. So if you look at the method theorem, you realize that we need to reduce the number of subproblems to 3. So this number should be 3. So once we have that, that would give us the n log 2, 3 algorithm. So So the original one is n log 2, 4, right? So that's the estimate time. So to reduce that from 4 subproblems to 3 subproblems, we'll be using the hint, right? The hint given in the question. So we say that x0 plus x1 times y0 plus y1, that equals to x0 times y0 plus x0 times y1 plus x1 times y0 plus x1 times y1. Right? So if you compare to what we had before, we would need these 4 subproblems, right? I mean, we would need x0 times y0. We would need x1, y0, x0, y1, x1, y1. So all these 4 subproblems are what we need to solve in the original naive algorithm. But if we look further, we realize that, okay, so for these 2 terms, they can be actually summarized as x1, y0 plus x0 times y1 times 10 to the power of n. So you simply group those 2 terms together. And it means if we need to calculate x times y, we would need to know x0, y0, x1, y1, and the sum of x1, y0 plus x0, y1. We don't need to know each one specifically. We only need to know their sum. Right? So, which means we just need this value, right? We just need this value. So if we rearrange this equation a little bit, we will have x0, y1 plus x1, y0. So this is what we need to compute, equals to x0 plus x1 times y1, y0 plus y1 minus x0, y0 and minus x1, y1. So, of course, this is a problem, it's another subproblem, and the third subproblem is just this one. So you have another multiplication subproblem. Right? And then we know that if x0 has n over 2 digits and x1 has n over 2 digits, the sum of them can be no more than n over 2 plus 1 digit. So when n is large, you will consider n over 2 plus 1. That's almost the same as n over 2. So in this case, we will still have both sides of the operators, the operands being n over 2. This is again a subproblem with the input size n over 2. So now we need to compute 1 subproblem, 2 subproblem, and 3 subproblems. Right? Everything else can be computed in linear time. So the addition of x0 and x1 can be done in linear time because addition, this can be done in linear time, and then the subtraction can also be done in linear time. So everything will still be absorbed into the final term, On. So in this case, Tn would be 3 Tn over 2 plus O. So that would, when you apply for the master theorem, would only give you O n log 2. Right? So that's for question, I think, 3. So question 4 and 5, you just whatever, read the slide and move it to the homework. I think I put it there because I want you to actually go over the slide. It's a thing very important. But there shouldn't be any like challenge for those two questions, 1 and 5. Any questions, other questions?
Could you like give an example for like what x0 and x1 would be for like a
Well, it's just the first half of the digit. So if you're talking about 1, 2, 3, 4, 5, 6, then this would be x0, 1, 2, 3. x1 would be 4, 5, 6.
Okay, what if it was like a single digit? What would it do?
Well, if it's single digit, then just put 0 before.
Okay, and 0 would be x0 and 1 would be x1.
Yeah,
Okay, anything.
Or if you have two numbers that with different digits, you will still pad the shorter one with the zeros ahead.
Okay.
So
Thank you.
if you're multiplying 1, 2, 3, 4, 5 with 68, then you just treat that as this one.
Okay, all right, thank you.
Yeah.
Can you explain what the three subparts of that last equation were again?
This one?
Yeah,
Well, this is for computing this value, right?
yeah.
So this value is for computing that, right? So we have x1, y1, we have x0, y0, so that's the same, right? Those are the same. So you will still have x0, y0, x1, y1. And then, so previously we need to compute this one and this one separately. So we have 4 subproblems. Right, so in the improved algorithm, we are trying to compute to infer the sum by only computing one extra subproblem. Because we've computed this two anyway, we have to do it anyway. So we need this one, and this one, and now we get this one. And then we can plug in the value of this one, and this one back to this equation to get the value of x and y.
Okay.
Any other questions? You guys want me to talk about homework question 1, like homework 6 question 1, or
Could you do question 2?
yeah, 1 and 2? Any for question 1? If we can do both, do you want to listen question 1 first or question 2 first? Well, 2 first. Okay, good. All right. So I think I want to talk about a little bit more to motivate the solution instead of just giving you the solution. So I'm not sure if you guys have learned like a more generic way to design recursive algorithm when you're running this pre-med course. So the general way is we are trying to think about if we have different parts of the solutions, how can we combine them, right? So which information do we need to obtain the solution of the current problem I need? So that's a key question you want to ask. If I break down my problem into subproblems, what information do I want to get from those subproblems to facilitate the computation of the current problem? Okay. So we know that we're given a set of prices for the stock, right? So then if we simply split them into half, so these are the former days, this is later days. What do we need to calculate the best trade challenge? What do we need from this subproblem 1, subproblem 2? So what information do we need? We want to obtain from those subproblems.
You want to have the lowest value before the highest value.
That's correct. So I can translate that out. We want the lowest value in subproblem 1 in the time that from the former half. We need the maximum value for the right half, right? And what else do we need? How about we just simply say, okay, if we're doing recursively, we want the max here as well, want the mean here as well. Okay, so do it very recursively. So what else do we need?
In this program, you're going to want within your subproblems the maximum problem that you can obtain.
Yes. So we want this optimal solution from this apartment as well, right? Because we can potentially buy here and sell there. We potentially buy and sell from the same half of the things, right? Right. So in that case, okay, so we just look at each property we need. So if we have a set of values, and then we split them into two halves. So, and we know the minimum of each one. How do we get the minimum of the entire one? Just a smaller one, right? Right, so the minimum value of both halves will just be the smaller value of the mean in this part and the mean in that part. So same for max, right? And then the optimal value for this one and that one can be solved recursively because it's the original recursion, the objective of the recursion function. So once we get the mean and get the max, we just need to compute max minus mean. So that is the optimal profit. Okay. If we buy in the first half and sell in the second half. Right, so that's the maximum, the max minus the min. Once we get that, we're computing. Let's say this is a OPT, cross. Say OPC, OPT1 and OPT2. So then we're gonna compare OPT cross with the optimal value of the first half, and compare that with the optimal value of the second half. Whichever is better, then that's the optimal value of the entire set. Right? So actually, the time complexity for that is Tn. We have two subproblems, right? T2, 2, and 2. And then we just need constant time. Because to compute mean, you're comparing two values. This one single comparison. When computing max, you're still comparing two max values. And when computing the optimal value, you are running one subtraction and then two other comparisons. So all of them can be done in constant time. So you have a 1 there. So the algorithm actually runs in log n time instead of O n. Right? Yeah.
What is the output of this, when you design a recursive algorithm? Are we looking to output maximum profit or just use days?
Well, you have to output all three.
Okay.
Because you will need all three information to get the correct. So in practice, of course, you can return as an object or like a structure. Right? But in Python, it's easy.
Yeah.
You can do that. Any other questions? Yeah.
So, sorry, can you just go to the very last step? How do you get a login equation?
Oh, I mean, if you simply, all right, so let me check the method theorem. I might be wrong in that case. So we have A equals to 2, right? And then B equals to 2, and C equals to 0. Okay. In this case, we have that. So it should be linear time. Right. Oh, when? have constant time right here, or 1, and that's n to the power 0, c equals 0. I mean, if you don't want to compute min and max recursively, you want to simply scan linear time scan through the entire set number, that would make this O n, and that would give you the m of n. So you don't need to do that. Right? Any other questions? Question 1, anyone? You guys solve question 1 already, or you want to listen to it?
Yeah, if you could still go over it, that'd be great.
So for question 1, we know that we have a set of numbers that are stored in 2 databases, right? So database 1, database 2. And then we're trying to find a median among those set of numbers. We can't merge them because they're too big. We can just simply probe database 1 or 2 to ask for it to return the kth value of the entire set. So the idea, I think, is more similar to the binary search that you have. You can see that from the time capacity, all right? So every time we're trying to, if you're trying to find the median, then of course we start with looking at the n over 2 value. So that's the best thing we can guess, right? So maybe asking DB1 to return the n over 2th value, ask DB2 to return the n over 2th value in the first place. Okay. So let's see. They are right here. Okay, so you have v1, value 1, and value 2. Well, the problem is that because the two databases are independent, you don't know, what kind of order or how to partition those numbers. Then v1 and v2, they might not be the same, right? You can't guarantee that those numbers are the same. So what we can see is when we compare the values, if v1 is larger than v2. Okay, what we can get is, of course, the true median can't be in this half, right? Because if the true value, if the median is right here, then that value is larger than, more than n over 2 elements in db1, and because v1 is also larger than v2, so that value will also be larger than more than n over 2 numbers in db2. So that numbers will be larger than more than n numbers in a total set of numbers, and it can't be the median. All right, so that's the same rationale as the binary search, but you just apply that individually in each database. Any question about that? So we're sure that the correct values must be in this range. So it means that we cut the original size of the database by half. Okay. So similarly, we know that the smaller half of the DB2 can't contain the true median, and it must be one numbers right here. Okay. So just do this recursively, and then the next one we probe something right here. So this would be n over 4, right? So this is actually n over 2 minus n over 4, and that equals to n over 4. So for this one, we're trying to probe something right here, so that's n over 2. So the original probing position plus half of the step size, and that's 3 over 4n. So realize that every time when we're trying to probe a different, or a set of different positions, we always keep the sum n. Right? So the beginning, we probe n over 2, n over 2, so the sum of those ranks of n. The second one is n over 4, and 3 over 4 times n. The sum of those ranks, again, being n. So we're always trying to find the nth value. That's the median, right, among these two n numbers. So the termination part here is, of course, when V1 and V2 being the same. So we know that they're the actual median, or if the step size right here is a step size reduced to 1. So you see that even those two numbers are different, we can compute their average, whatever, pick either one as the median, because we cannot go further. Okay, so that's the idea. Does that make sense? So in this case, as we see that every single probing or every pair of probing in this 2K for both of the bases will reduce the size by half. So it's easy to conclude that it takes longer before you either pre-terminate when you have V1 equals to V2, or you reaching the step size of the 1. Any other questions? I think so that covers homework 6, Q1, Q1 through Q5. Any other questions? No. So, well, again, please help me fill up the form for the evaluation. So the department has been trying to improve the response rate that they have. It's very important for both department and myself. You know, we try to use the comments for you guys to improve our future teaching. So please help me fill that up, and that'd be very helpful. If no more questions, any last minute questions? We still have time. Yeah.
Are there any things that we covered that you're not going to test on the final? Like you said, the generic form for the linear homogeneous recurrence. Is there any?
Right. So I think we're not going to cover the formal proof. So I won't require you to cover formal proof. I will require you to compute the more complex form of the linear homogeneous and non-homogeneous equations. Other than that, think about it. I won't ask you to work on the proving one rule, the original inference rule is correct. I won't ask you to prove multiple is correct. I won't ask you to convert one English sentence into its symbolic form. I won't be testing truth table, those things, the fundamental things relating to the discrete math. But the other ones, I think they could occur in the lab. So homework 1, those fundamental things is unlikely to occur in the lab. And the form of the final would more be like a midterm, as I said, right? So for example, if I wanted to solve a recurrence, so I won't say this is I won't ask a question like Tn equals to 5t and for whatever plus O n squared and solve it. I won't ask those questions because I think it's something not matching our learning goal. I'll be giving you one potential error, and then you will have to find out the growth function recursive form by itself and solve it. So it will be more like the midterm. So I have a question from the chat, I guess. No formal proof, yeah, no formal proof. No, I didn't say no homogeneous recurrence. So no higher degree homogeneous recurrence. So what was your question for homework question 2? Let me know a more specific question. Which part do you think? So I show the slide, so which part do you want me to go over again? I have a question about the calculation of the mean, the max, the optimal value, the time complexity, like which part? Yeah, sure.
Will we cover combination permutation?
Would be. All right, so if you, well, you can ask me after, and I'll figure out how we will recurse through it. Well, so you have two subproblems, right? So, I mean, you will have to calculate all these three values. All these three values, so the mean, the max, the optimal value. So to recursively calculate mean, so the actual mean of the the whole set n would be the minimum value of the mean of n over 2, right? And the minimum value of the other n over 2. Right, so if you split if you split a set of numbers to two subsets, the minimum value of the entire set will be the smaller number of the minimum value of the first subset and the minimum value of the second subset, right? Same for max. And then for the optimal value, you're going to compare with the maximum profit you gain from the first part, the maximum profit you get from the second part, and then the maximum value you get from crossing these two parts, meaning you buy the first part and sell the second part. And whichever is larger, that's your solution. All right? Any questions? Any other questions? Does it make sense? I'll see if some reply. All right.
On the last part of the slides, the optimal substructure and direct acyclic graph, what kind of questions?
So I won't test anything about optimal substructure. Right, as I said in the previous lecture, so everything before the optimal substructure will be tested. I mean, it's likely to be tested, but nothing from optimal substructure because you haven't gone through that completely. You need to know the relation. You need to know subproblems. You need to know the rest of stuff like theoretical cyclic graph, topological ordering, and so on and so forth. But we won't cover the optimal substructure in exam.
Can you explain how you can find the min and max in constant time?
Well, I mean, if you simply, well, I mean, imagine you start with two numbers. And you know the max, of course, you know the minimum of the first one, the minimum of the second one. And the minimum will be just the smaller of those, right? So it's a constant time.
Nice.
And then, so that applies the same right here. You have for one constant time for finding the mean, and you plug in that, it takes, mean time.
Okay, so you're carrying information around with you through the subcalls, because in general, if you're just given a list and you have to find a min, that's not constant time, right?
Well, if you think about it, you're trying to find the minimum of a set of numbers, it's a constant time.
Right.
Either by dividing into subproblems or just simply scan through it.
Okay.
It's linear time, right? If you so
I see.
it's a recursively done, and then recursion it takes constant time, but when you build up the entire recursion, it takes linear time. Any other questions? We still have time. 5 or 10 minutes.
What would be a good example, either in the homeworks or in the midterms, of like a good informal proof? Do you know?
So what's the question with the? On what's,
Again, either in the homework or the midterm, like what would be like a good like example of like a good informal proof?
so we won't test formal proof in the finals, I'm not sure.
Yeah, informal proof.
Informal proof, so what kind of example that we will have as informal proof, is that the question?
Yeah.
I mean, you can look at like the slides, given the slide, right? So we have informal proof for, I think I should start with, we have the informal proof, like, also from the book for the Gale Shapley side with them, we have the informal proof for, like, what's that, the lower bound, right, for comparison-based sorting, and so on and so forth. So those examples you might want to look at. All right, and no more question, then I think let's end right here. Thank you very much. So very happy and proud to have you guys be my students. And, question?
So, just wanted to, what happens to the signing? I think.
Good. Can you see louder?
No, I'm asking about the signing, the final signing for the course.
The final signing.
Yes.
We have already done 5 signings, so we don't sign for the final. But you have to come here though. It's not about signing. It's not about the final itself. That's fine.
And the finals on Wednesday?
I think, yeah. So let me confirm. You know.
Yeah, I thought it was on Friday.
No, it's
I think it's Wednesday.
7:30 a.m.
Thank you.
Second.
Yeah, get up even earlier for this class. You gotta love that.
Yeah, Wednesday.
I might just show up
Yeah,
the
so
previous
yeah,
night.
8 o'clock,
Yeah,
Tuesday,
sneak in
Thursday.
this room. Yeah.
Yeah, exactly. So Wednesday, May 11th, 7:30 to 10:30 a.m. right here in this. All right, thank you very much, and have a nice